first. Okay, given the zeros, write a polynomial function of least degree with integral coefficients. So they've given us the zeros of 2, 4, and -1. Your binomials that you use will always be the opposite. So it's what would make it 0 is what they've given you. So if they gave you 2, then 2 would make x minus 2 0. So your binomials will always be opposite of what they gave you. So your binomials for these three would look like this: x minus 2, x minus 4, and x plus 1. Those are your binomials for this polynomial. And if they want you to actually find the polynomial based on these binomials, you just FOIL. Like, that's all you do. And so if you FOIL these two, you would say x times x, x times 1. -4 times x, -4 times 1. I would simplify that before I distributed that x minus 2, so I'm going to simplify those to make it x squared minus 3x minus 4. And then I'm just going to distribute that x and -2. So I'm going to distribute the x through x to the third, 3x squared, 4x, distribute your -2, -2x squared, positive 6x, positive 8. And combine your like terms. This one doesn't have a like term. Combine these two. This one doesn't have a like term. And you would get something like that. X cubed minus 5x squared plus 2x plus 8. That is the polynomial. Graphing polynomial functions. We're going to talk a little bit about graphs and what happens. And this is just leading you into more polynomial functions later down the road. So these are some of the ones we've already talked about. We already know what a constant looks like, a horizontal function. That's just y equals a number. We also know what a linear function is, y equals mx plus b. All right. We know quadratics. That's what we did this chapter, believe it or not. Seems far away, but we've done quadratics. X squared plus bx plus c. That's a quadratic. Cubic. We have started looking at cubic functions in this, and these are what the graphs look like. You'll notice my parabola does this, and then my cubic has another turn in it. My quartic has yet another turn in it, and my quintic, my 5 degree, has yet another turn in it. And so you start to see that the more zeros you have, the more turns you have, which makes sense because a 0 is where it crosses the x-axis or bounces off the x-axis, depending on the equation. And so that makes sense that you would see more turns. In order for it to have zeros, it must hit or at least cross one of the x-axis. So that's why you're starting to see those turns. Depending on the type of equation or where those squares and cubes and all are, will determine where it turns and how high it goes, and all of that good stuff. But this is what they look like. This is kind of a generic, and they've given you what the actual functions are down here. You can see that they're not just standard x squared functions. You know, they have a little plus or minuses to show you the nuances in them. And you don't really need to recognize them at this point. These three, you should know, though. Those three you should know. There are some things that tell us a little bit about these functions. One of the things we can always know about a function is what happens at the end of the function, all right? So there are 4 options here that a function can do. At the very end, both sides can go up, similar to this parabola here. Or at the end, both sides can go down. This is actually a degree of 4, but both sides go down here. They can go opposite directions. Either they can go down and up or up and down, right? So they can be continually going up or continually going down left to right, okay? So then what makes it do that? There's actually 2 things we look at to decide what's going to happen to the function. These first 2 have even degrees, okay? By that, I mean the highest exponent is an even number, 2, 4, 6, 8, 10. We all know what an even number is. You'll notice that the even numbers went the same direction. The ends went the same direction. So then what tells us whether it's going up or down? Now we're going to look at the leading coefficient. So the number that's right in front of what tells me what degree I am, we're going to look at that. If it's positive and even, both of these ends will go up. If it is negative with an even degree, both of the ends will go down. All right? So then these 2 are odd. We have an odd degree. So this is 3, this is 5. All right? So anything with an odd degree is going to go different directions. If it's positive, and odd. It will be down on the left, up on the right. So you can think of it as continually going up, all right? This notation here is telling you what's happening with x and y. So as x is going to negative infinity, y is going to negative infinity. As x is going to positive, y is going to positive. That's what this means. Another way to say is that down on the left, up on the right. Up on the left, down on the right, okay? So for now, I will take this, where you can just tell me both ends go up, both ends go down. It goes down on the left, up on the right, up on the left, down on the right. I'll take this notation. Next year, if you take pre-cal with me, you will be doing limit notation. So, but for now, we're going to do this kind of notation for this chapter right here. All right? The two end behaviors of an even degree polynomial are similar. These functions have an even number of real zeros. The fact that the graph is tangent to the x-axis of the origin indicates that 0 is a double root of the function. Right here is talking about this one. Polynomial functions of odd degree must have at least one real zero because their two ends are opposite, okay? So by real, remember we had imaginary roots when we did, like we did the cubed, x cubed minus 8. Remember we ended up with an imaginary number at the end because we had a negative in our root, okay? What this is saying is that if you have an odd degree and it's going different directions, then you had to have crossed the x-axis at least once at a real number, okay? Whereas you can't guarantee it with these guys, all right? Because he never crossed the x-axis. He actually didn't have any real zeros for sure because he never crossed the x-axis to get one. But these have to. If they go all the way from infinity to negative infinity or negative infinity to positive infinity, they have to at one point cross the x-axis. And that's what this is saying. So the negative also tells you you have at least one real number when you talk about zeros. So on our bell work or on homework, when you had x cubed minus 8, we had one real, right, which was 2. And then we had two that were imaginary, the plus or minus the square root of 3, negative 3, right? And so that one had at least one. It was a cubed root, 3 degree. It had to have at least one. Had to have at least one. So that's what that's telling us. Let's look at how this would be questioned, okay? How would a question be worded here? State the function's end behavior and describe the number of complex and real zeros. All right? So for end behavior, the first thing we're going to do is we're going to look at this. It is odd. Odd tells us that it's going to go opposite directions, okay? And then we're going to look at what's in front. What's in front of it is positive. It's a positive 1. So we know it's going to go up, meaning from left to right. If you were to write it in the shortcut, on the left side it would be down, and on the right side it would go up, all right? So the graph would do something like this. We don't know exactly what it would do, but it would do something like that. Down on the left, up on the right, okay? So this is actually the first answer. State the end behavior. Down on the left, up on the right. And we know that from the degree and the coefficient, all right? Describe the number of complex and real zeros. All right, complex zeros. That will always equal the degree. Always equal the degree. So the number of complex zeros here is what? What is my degree?
3.
Yeah, so I have 3 complex zeros. All right, it's always going to be what my degree is. Those are going to include real and imaginary. That's what that means by complex, real and imaginary. Then it says, what can you say about real zeros? For real zeros, because it's odd and I know that it has to cross the x-axis, then I know that it is at least one. At least one real zero. All right? All right, graphing. So let's just talk about the graph really quickly. Anytime I ask you for zeros when it's like this, one of two things will be true. Either you'll be able to factor by grouping like this, or I will give you a 0. All right? So I'm not going to make you try all the numbers and try to figure out at this point. I'll either give it to you, give you a 0, or it will be factorable by grouping. All right? All right, so in this case, it's not factorable. How would I know that? Well, if I grouped this, I would get x minus 2. If I grouped this, I would get 5x plus 6. That's not factorable by grouping, okay? So in this case, I would say I'm going to give you a factor, or I'm going to give you a 0. And I would say, okay, a factor of this guy would be x minus 1. So I know that my 0 is going to be happening at 1. So then I can use synthetic division here. I can say, okay, if this is a 0, then when I do synthetic division, my remainder should be 0. That's what it means. So if I do synthetic division, I should get a remainder of 0, and I do. All right? So I do know that one of my zeros has been given, and it happens at 1. All right? Then I'm going to say, well, how do I find my other zeros? Well, the way I find these is I can factor if it's factorable, or if it's not, I can use the quadratic formula. All right? In this case, this is factorable. There's factors of 6 that add up to 1, or subtract to give you 1. What are they? This is going to be x squared minus x minus 6, right? So I can say x minus 3x plus 2, right? And so I have another 0 that happens here. What is going to make that group 0?
Just plus 3.
Positive 3. And what makes this 0?
Negative 2.
Negative 2. So I have 3 zeros, and they're all real. And that's as many as I'm going to have because my degree was 3. So that tells me all of my zeros, all right? Next, I can say, well, all right, I know where my zeros happen. How do I get to them? How do I get to those zeros? So I'm going to look at end behavior. End behavior. Are they going to go the same direction or opposite directions? Opposite. It's odd. And is it going to go up from left to right or down?
Up.
Yeah, so on the left side, I'll be coming from negative infinity. It's going to be pointing down on the left side. And on the right side, I'm going to be going towards positive infinity. So that means my lowest 0, negative 2, is the first one I'm going to come to. And I should be coming up, right? Up to negative 2 on the x-axis. Somewhere along the way, I'm going to have to turn because I also have to cross the x-axis at positive 1. And then somewhere down there, I'm going to have to turn again because I have to cross the x-axis again at positive 3. So does everybody see how this is going to help me sketch the graph? Right? And so if I were to sketch this graph without any help other than this, I could say, well, I know a couple things that will happen here. So we're going to just sketch it at this point. If I were to sketch it, I would say, all right, the first thing I'm going to do is plug in my zeros. I have a 0 at negative 2. I have a 0 at positive 1. I have a 0 at positive 3. Zeros are the same thing as x-intercepts. I know that somewhere down here, I'm going off to negative infinity, and somewhere up here, I'm going up to positive infinity. One more point will help me a little bit, and that's my y-intercept. Y-intercept is just if I plug a 0 in for all of these. So plug a 0 in for your x, I have 0 minus 0 minus 0 plus 6. So I also have a y-intercept up here. All right, that sometimes helps as well. And so when I graph this, I'm going to say, well, I'm going to start down here. I have to cut through that negative 2. I have to cut through that and turn. Somewhere down here I have to turn, and I have to go back up to infinity. My end behavior, I know this because of what happens here. All right, and I don't know why it just erased my graph, but we'll draw it again. So first, my end behavior helps me because it tells me I'm starting from down here. I have to cut through at my 0. I also have to cut through at my y-intercept, cut through at a 0. Somewhere down here I have to turn because I have to cut through my x-axis again. And I know at the very end on this side I'm going towards infinity. So even if it's not perfect, I know that it's close. In fact, if we look at the actual graph, it looks like that. All right. So even if you don't know the exact turning points, which you don't have to know just yet, you do know that you're going up through your zeros. You're going to turn, you're going to cut through your y-intercept, cut through your 0, turn somewhere, cut through your 0 again. All right.